Now that we've reminded ourselves of what an equilibrium constant is, there's some properties of equilibrium constants that we can take advantage of when we're dealing with multiple reactions. Let's say, for example, we have an acid dissociation reaction. We'll see lots of these this semester. So we have, say, a weak acid HA dissociating into protons and the anion. And then we have a different reaction where we have a proton adding to some molecule C, not carbon here, but just trying to do this in a generic way. And so each of these will have an equilibrium constant, right? So we'll have K1 and K2. And we can write out these equilibrium constants. So remember, we take products. So H plus times A minus divided by reactants, HA. And if we had actual values to go in here, these would all need to be in molarity. These are all things in solution. It's not explicitly stated, but these all should have the aqueous tag next to them. When we're thinking about acids and bases, those are only defined in aqueous solution, basically. K2, we can also write down that equilibrium constant, CH plus divided by H plus times C. Remember, it's always products go on top, reactants go on the bottom. And since all of these have stoichiometric coefficients of 1, we don't have any exponents on any of these in this particular case. What if we add these reactions together? So if we take reaction 1 plus reaction 2, well, we can go ahead and do that. So we would just have HA plus H plus C in equilibrium with H plus A minus plus CH plus. And we have an H plus on either side, so that'll cancel out. And so our net reaction is HA plus C in equilibrium with A minus plus CH plus. So it's classic acid-base reaction here. Now, what about the equilibrium constant for this reaction? Now, we added the reactions together. Does that mean that we add the equilibrium constants together? Well, let's look at that. So if we have K1 plus K2 here, that doesn't seem like it's going to match up. We'll have two separate fractions. Things aren't really going to work out. Because we can write out K3. We know what it is already. Because we can just take the reaction, our net reaction at the bottom here, do products over reactants. A minus times CH plus divided by concentration of HA times concentration of C. And we can see that if we add K1 and K2, that does not equal K3. Right, so K1 plus K2, I'll write this in red, does not equal K3. That doesn't work. So let's see what we could do instead. Maybe we multiply them. So we take K1 times K2. So let's actually go ahead and just write this out. We have H plus A minus divided by HA times CH plus divided by H plus over C. And we can see that our H pluses are going to cancel, and you can already see this is similar to what happened with our reaction. And our net result is A minus times CH plus HA over C. That is equal to K3. So this is a check mark here. So when we add reactions, we can multiply their equilibrium constants and know that so if we know, for example, the numerical values of K1 and K2, that allows us to find the numerical value of K3 without needing to do any measurements on that third reaction. Very convenient. Similarly, if we subtract reactions, we divide the equilibrium constant. So if instead of adding here, right, so instead of adding these reactions, if we subtract reactions, divide the equilibrium constants. Okay, and so that's some basic manipulations that we can do with equilibrium constants that allow us to find values for equilibrium constants even if we don't necessarily have measurements. If we have measurements for different reactions and can reconstruct our reaction, we can still find the equilibrium constant.